Hello everyone, welcome back to another lesson in our digital system series. In this video, we are going to continue our study of Boolean Algebra. In the previous lesson, we covered the main Boolean operations and how Boolean expressions work. Now, we'll move on to an essential part of Boolean Algebra, the Boolean laws and rules, which allow us to simplify expressions and prove equivalences. Understanding these laws and rules is extremely important because they form the foundation of everything we'll do later on truth tables, canonical forms, kernel maps, circuit simplification, and more. So stay with me to the end and follow each step carefully. This lesson is fundamental for all the upcoming videos. Alright, before we continue, it's important to mention that this lesson builds directly on lesson 3.1. If you haven't watched it yet, I strongly recommend doing so first, since we'll be using Boolean operations to evaluate expressions, assign logic values, and prove equivalences throughout this video. Okay guys, before we begin, here's a general overview of the most common Boolean laws and rules. In the left column, we have the three main Boolean laws: Commutative Law, Associative Law, and Distributive Law. In the center column, we have 12 Boolean rules, widely used to manipulate and simplify expressions. On the right column, we have the Morgan's theorems, which will be covered in their own dedicated videos. In today's lesson, we'll focus on the three main laws and the first 9 rules. The last 3 rules, 10, 11, and 12, will be explained in the next lesson, since they require the knowledge we're building today. Feel free to take a screenshot of this table. It'll help with exercises and future lessons. Now let's begin with the first law, the commutative law. This law states that in Boolean algebra, the order of the terms does not change the result for Boolean addition and Boolean multiplication. In other words, A plus B equals B plus A, and A times B equals B times A. Now let's prove this by assigning logical values to the variables. Let's test some possible combinations of A and B. For example, let's test 0 to the variable A and 1 to the variable B. So according to the pattern of Boolean addition, 0 plus 1 equals 1, and 1 plus 0 equals 1. So as you can see, we reach the same results for both sides. Okay? And the same thing happens to Boolean multiplication. Let's assign the same logical values to their variables. For example, 0 times 1 equals 1 times 0. According to the pattern of Boolean multiplication, 0 times 1 is 0, and 1 times 0 is 0, like this. We reach the same result for both sides. Okay? Let's try another possible combination. For example, let's assign logical value 1 to the variable A and 0 to the variable B, like this. 1 plus 0 equals 0 plus 1. Performing the operation, 1 plus 0 is 1, and 0 plus 1 is 1. In this case, we reach the same result for Boolean addition. Let's use these logical values to the Boolean multiplication. 1 times 0 equals 0 times 1. For both sides, the value is 0. The results match. And that's why I said it's extremely important to watch the previous lesson, because in the previous lesson I explained how the Boolean operations works there. So the commutative law tells us that in Boolean addition, swapping A and B makes no difference. In Boolean multiplication, it also makes no difference. This property is essential for rearranging and simplifying Boolean expressions. Now let's move on to the associative law of Boolean algebra. This law states that the way we group the variables in expressions does not change the final result, both for Boolean addition and Boolean multiplication. So we have, for Boolean addition, A plus B grouped inside the parentheses plus C is equal to A plus B plus C inside the parentheses. To make this clearer, let's test just a few combinations. No need to check every possible case, otherwise the video becomes too long. The important things here is understanding the idea. So let's choose some examples with Boolean addition. For example, let's choose this combination, that is 0 to the variable A, 1 to the variable B, and 1 to the variable C. Now let's assign each logical value to its corresponding variable in expression, like this. Now let's perform the operation. Pay attention. According to the order of precedence, Just like in mathematics, we first evaluate what's inside the parentheses. 0 plus 1 equals 1, and we repeat plus 1, okay? And the same thing happens to the right side. First, what's inside the parentheses? 1 plus 1 equals 1, and we repeat the 0. Let's continue the operation. 1 plus 1 equals 1, and 0 plus 1 equals 1. So, as you can see, we reach the same result for both sides. Let's test this combination. 1 to the variable a, 0 to the variable b, and 1 to the variable c. Performing the logic operation, 1 plus 0 is 1, and 0 plus 1 is 1. We repeat the other values. And let's continue. 1 plus 1 is 1, and on the right side, 1 plus 1 is 1. Again, you'll reach the same result. So, the associative law is valid for our operation. Now, for Boolean multiplication, the associative law states the same thing. A times b grouped inside the parentheses plus c is equal to a times b times c grouped inside the parentheses. Let's do the same thing. That is, let's test some possible combinations to evaluate the expression. For example, 1 to the variable a, 0 to the variable b, and 1 to the variable c. Now let's perform the operation. 1 times 0 is 0 times 1. On the right side, 0 times 1 is 0 times 1. Let's continue. 0 times 1 is 0, and 1 times 0 is 0. As you can see, you reach the same result for both sides. Okay? Let's test other combination. For example, 1 to the variable a, 1 to the variable b, and 1 to the variable c, like this. Performing the operation, 1 times 1 is 1, and 1 times 1 is 1, like this. Let's continue. 1 times 1 is 1, and 1 times 1 is 1. So, again, we reach the same result. So, the associative law for Boolean multiplication is valid. Now, let's move on to the third fundamental Boolean algebra law, the distributive law. It states that a times b plus c grouped inside the parenthesis is equal to a times b plus a times c. Okay, before we prove the equivalence by assigning logical values to the variables, let's take a moment to understand how the distributive law works. If you look at this expression, notice that the variable a is being multiplied by b, resulting in the term a times b. In the same way, the variable a is also being multiplied by c, resulting in the term a times c. These two products are then combined using the OR operation. So what the distributive law does is distribute the variable a across each term inside the parentheses. Now that you already know how the distributive law works, let's prove the equivalence by assigning logical values to the variables. We don't need to test all the possible combinations. Just a few examples show that both sides are equals. Using this possible combination, that is 0 to the variable a, 1 to the variable b, and 0 to the variable c, like this. Performing the operation, and remember, we first evaluate what's inside the parentheses. On the left side, 1 plus 0, and on the right side, we first evaluate the multiplication, just like mathematics, and then the addition. On the left side, we have these values, 0 plus 1, because 1 times 0 is 1, okay? On the right side, just like I said, we first solve the AND operations. 0 times 1 is 0, and 0 times 0 is 0. Continue the operation. 0 times 1 is 0, and 0 plus 0 is 0. So, the same result for both sides. Now let's use this possible combination. 1 to the variable a, 1 to the variable b, and 0 to the variable c. Performing the operation, on the left side, we first evaluate 1 plus 0. On the right side, 1 times 1 and 1 times 0, like this. Now, 1 times 1 is 1, and 1 plus 0 is 1. Again, both expressions produce the same result for both sides. One of the biggest benefits of mastering the distributive law is that it allows us to simplify logic circuits, as shown on the slide. On the left, the expressions a times b plus c requires one OR gate plus one AND gate, totaling 2 logic gates. On the right, the expression a times b plus a times c requires 2 AND gates plus 1 OR gate, totaling 3 logic gates. So by applying the distributive law in reverse, we reduce the circuits from 3 logic gates down to only 2. This results lower cost, lower power consumption, reduced propagation delay, cleaner and more efficient designs. And this is why understanding Boolean algebra law is essential when designing and optimizing digital circuits. Don't worry, in another video, I'll be teaching how to build a logic circuit from Boolean expressions. Remember, the goal here is to learn about Boolean algebra. So far, we've studied the 3 main Boolean laws: the commutative, associative, and distributive law. Now, let's move on to the Boolean rules. These rules are practical tools to help us manipulate, simplify, and transform Boolean expressions more efficiently. Let's start with the rule 1. This rule states that any variable added to 0 results in a variable itself. This operation uses the OR gate, since this symbol represents logical addition. The 0 does not change the logical value of A. Let's test 2 possible values of A to confirm. If A equals 1, then 1 plus 0 equals 1. So, according to the pattern of Boolean addition, as you can see, the result is the same logical value assigned to the variable A earlier. And if A equals 0, then 0 plus 0 equals 0. In both cases, the result is A confirming the rule. Let's take a look at the second rule. It states that any variable added to 1 results in 1. Again, this is an OR operation. With the OR gate, if any input is 1, the output will be 1, no matter what the other input is. Let's confirm this rule testing the values. If A is 0, so 0 plus 1 equals 1. And if the variable A is 1, so 1 plus 1 equals 1. It's like I said, no matter what the other input is. If at least one of its input is 1, the output will be 1. In both cases, the result is 1 confirming the rule. Now let's take a look at the rule 3. This rule states that when we AND any variable with 0, the output is always 0. In other words, 0 is the dominant element of the AND operation. So let's confirm this with both possible values of A. If A equals 0, so 0 times 0 equals 0. And if A is 1, 1 times 0 equals 0. No matter what the variable A is, the result is always 0. Now let's analyze the rule 4. These rules tell us that when we AND any variable to 1, the result is always the variable itself. Let's test the possible values. If the variable A is 0, so 0 times 1 equals 0. And if A is 1, so 1 times 1 equals 1. So in both cases, the result is the variable itself, confirming the rule. Let's take a look at the rule 5. The rule 5 states that a variable added to itself equals itself. Here we are dealing with Boolean addition, which corresponds to the OR gate. Let's confirm this with both possible values of A. If A is 0, so 0 added to itself results in itself. That is, results in 0. As you can see, the output is equal to A. The rule 6 is one of the most fundamental rules in Boolean algebra. It states that a variable added to its complement is equal to 1. Notice that A bar represents the complement of A. Since the OR checks if at least one input is equal to 1, combining a value with its opposite will always produce 1. Let's confirm. If A is 1 plus its complement, that is 1 plus 0, is equal to 1. And if A is 0, so 0 added to its complement, that is 0 plus 1, results in an output 1. In both cases, the result is 1. So, the rule 6 is verified. Let's analyze the rule 7. The rule 7 states that a variable multiplied by itself results in itself. Here we are dealing with Boolean multiplication, which corresponds to the AND gate. This rule tells us that ANDing a variable with itself does not change the result. That is, it remains the same variable. Let's confirm with all possible values of A. If A equals 0, so 0 multiplied by itself results in itself. That is, 0 times 0 equals 0. And if A is 1, so 1 multiplied by itself results in itself. That is, 1 plus 1 equals 1. That is, the output is always equal to A. Rule 7 verified. Let's move on to the rule 8. The rule 8 states that any variable multiplied by its complement is always equal to 0. Remember, a bar or a negated represents the complement of a. That is, it is always the opposite value. When you AND two opposite values, that is, one is 0 and the other is 1, the result is always 0 because the AND operation only outputs 1 when all inputs are 1. Let's verify. If a is 0, so 0 multiplied by its complement results in an output 0. And if a is 1, 1 times its complement is equal to 0. So in both cases, the result is always 0. So, rule validated. And finally, let's move on to the rule 9. The rule 9 states that double negation brings the signal back to its original variable. In other words, if you invert a variable and then invert it again, you get the variable back. This is exactly the behavior of two NOT gates in a sequence. The first NOT gate flips the value, and the second NOT gate reverses it again. Let's verify using logical values. For example, if a is 0, when the logic 0 passes through the first NOT gate, it will be inverted to its opposite, like this. So the first NOT gate turns the 0 into the 1. And then, when it passes through the second NOT gate, it will be inverted again, like this, turning back to its original logical value, as you can see. And if a is 1, when it passes through the first NOT gate, it's inverted. And then, when it passes through the second NOT gate, it's inverted again, turning back to its original logical value. Okay? And that's why when we find a double negation over a variable or over a term, we can cancel out, like this. Therefore, a variable negated twice is equal to itself. In today's video, we studied the main Boolean laws and the first 9 Boolean rules, and we learned how to apply them to simplify Boolean expressions and prove the equivalences step by step. It's important to remember that these laws and rules are not meant to memorize mechanically. The real goal is to understand how they work and when to use each one. This foundation will be essential for everything we'll study next, including truth tables, canonical forms, kernel maps, and logic circuit simplification. If any part of this lesson was unclear, pause the video, go back, and review the explanation carefully. Boolean algebra becomes much easier with repetition and practice. In the next lesson, we'll continue this topic by studying the last Boolean rules, that is, 10, 11, and 12. These rules involve expressions with multiple variables and require the concepts we built in this video. If this lesson helped you, don't forget to like the video, subscribe to the channel, and share it with anyone who is studying digital systems or computer engineering. And if you have any question, leave them in the comments. I'll be happy to help. Thank you for watching, and I'll see you in the next lesson.